But let's go into detail of what do these three steps actually mean. So first, the free body diagram. Now, there's going to be rules of when can we say something is a free body diagram versus just simply a diagram. And also, when do we use a free body diagram? Well, anytime we are working on an equilibrium problem, so that's pretty much every problem in this course, and problems you're going to see even when it's not an equilibrium, if it's a dynamics type of problem, also a free body diagram is going to be crucial. So this is our first interaction with what is a free body diagram and what does it need to contain. So if we are drawing a particle, what does a free body diagram look like? So first, we need to select an object of interest, or really for a particle, it's going to be a point of interest. So that's going to be the centerpiece of this diagram is what's the point that we're analyzing. And we're going to draw it, and it's going to be freed from all of its connections, all of its supports. So as we're going to see in some examples, we have a lot of points that are going to be connected to ropes or cables or have a force acting on it. In the picture, we're going to start by just representing that particle or that object that we're going to be analyzing without any connections to it. Then we need to explicitly establish a right-handed coordinate system. Now typically we're going to use x right and y up as the positive directions when we're in 2 dimensions, and usually that's going to be good, but never assume that that is the coordinate system we're using. You want to make sure that you explicitly include it in the free body diagram, because later when you're talking about x direction, y direction, or the I component and the j component, that is always going back to the coordinate system that you have established for this problem. Because there might be problems, less commonly, but there might be problems where you want to use a rotated coordinate system, or for some reason you want x up and y to the left. So always explicitly include the right-handed coordinate system you're using for the problem. Now, in step 1 of this, we have our object freed from its connections. Now, the third piece of a free body diagram is we need to represent what did those connections do to our object or our point of interest. So all of the things it was connected to for particle equilibrium, we're applying some force on the object of interest that we are keeping. So if it was connected to a cable, we need to represent what was that cable doing to our object of interest. If it was a rope, if it was touching the ground, what did the rope, what did the ground do to our object of interest? So all forces acting on our object, we are going to symbolize using a single-headed arrow, where the direction of the arrow is the direction that connection, the direction of the force that connection had on our object. Always in this step, we are including what did those supports or what did those connections do to our object of interest. It is not what did our object of interest do to those connections. So for example, if there were a rope connected to our object, well, ropes can only pull, so the arrow must be symbolizing the action of the rope pulling on the object. And finally, we need to include dimensions here. So in 2D, commonly we are going to need to include angles or angle measurements as measured from the coordinate system that we've established. Or alternatively, we might find a ratio triangle useful, again, to establish the direction of forces or distances in our picture. And or it might be useful to use actual coordinates. Basically what the dimensions are going to be used for is establishing the direction of our forces, because we're going to need that information in later steps to know how much of a force was in the x direction, how much is in the y direction. So we're going to be decomposing these forces, we're going to be summing them in the x and the y direction as we saw on the previous slide, so those dimensions are going to be crucial. So how detailed does this diagram have to be? Well, kind of a general clue that you have enough on your free body diagram is if your free body diagram is drawn and you can really solve the rest of the problem from the free body diagram, you don't need to go back to that original picture, you have enough information on the free body diagram that it is complete. Now there might be times there's something you forgot to label in the free body diagram right away. You start working the problem and you realize, oh, you know what? I never established the direction or the angle that this force was pointing. So yeah, it's okay to go back, add that to the free body diagram. But all the equations you derive, all the equilibrium equations that you derive, must come from and agree with your free body diagram and the coordinate system that you established in that free body diagram. Okay, so we have a free body diagram, a complete free body diagram with all the information we're going to need for the rest of the problem.